Welcome back, everybody, for your second physical science lesson of the week. I pretty much took care of all housekeeping items on Monday. If for some reason you missed that video, but you want updates about our online classroom for the week, please go back and watch our video from Monday. We're continuing our objective this week of describing different variations in physical properties across the periodic table. We're going to be doing some review of the trends on the periodic table, and since today's lesson is a little bit shorter, if you need time, you should have time to finish the periodic trends activity that we started on Monday. Both that activity and a little self-quiz we're going to do at the end of this lesson are due by the end of the day on this Friday. If you have your bonding take-home packet out, we are now on to assignment number 4, titled Wrapping Up Trending plus Self-Quiz. It should look like this, and you should take out that material for today because we're going to start by taking a few notes on the front side of the piece of paper. So during our last lesson, the main two things we learned about were ionization energy and atomic radius. To refresh our brains on what those are, ionization energy tells us the minimum amount of energy required when you're wanting to remove an electron from an atom or molecule. This really helps us when we're forming ionic bonds between atoms. The atomic radius tells us the size of the atom. This usually means it's the typical distance from the center of the nucleus to the outermost boundary where the last valence electron is in the outermost energy level. To review ionization energy a little bit more, it always has to do with the valence electrons that are being removed. It is much easier to grab a valence electron from the outermost level of an atom than it is to dig deep further in. Some trends that we learned by graphing ionization energies on Monday is we saw that the further an electron is from the nucleus, the easier it is to pull away. This means that generally on the periodic table, as you move up and to the right, ionization energy increases. When you're up in the right-hand corner, it takes a lot of energy to remove an electron from the outermost energy level. When you're in the bottom left of the periodic table, it doesn't take as much energy to remove those valence electrons. For the atomic radius, we were able to map out using rulers and centimeters a general model of the radius of about the first 15 elements on the periodic table. What we saw is that as we move down on the periodic table, atomic radius increases, and as you're moving to the left of the periodic table, you're also seeing an increase in atomic radius. So our general trend here is atomic radius increases down and to the left.
Whether you've left school or you're still at school, you can appreciate the sheer fun and mayhem that chemistry can be. There's so much to it. Bunsen burners, mixing chemicals. Very nice. Now, you may have been allowed to mix very small amounts of lithium with water. You may, if with a responsible adult, have mixed H2O with sodium. And you may, under very strict scientific control, have witnessed potassium mixed with water. But the odds are, if you have, it will only ever have been on one of those rubbish science videos. There you go, mate, present. Oh, thank you very much. These next two are the dog's nuts of the periodic table. They are, if you like, the king and queen of alkali metals. Mix these babies with water, stand well back, and watch the mayhem. And that's just what we're going to do. Mr. Tickle, bring on the rubidium.
Here it is.
Is that it?
Well, it might not look like much, Richard, but it's a highly reactive metal. It's sealed in this glass tube under argon atmosphere conditions, just for safety.
Right, so what's going to happen when you drop that in the water?
Well, imagine, if you will, letting off a hand grenade in a bathtub.
Righto, I'm off. Have that.
Okay.
Good luck. Okay, Tickle. Drop the rubidium in the water.
Stand back, everybody. This one's going to be bad.
2 grams of rubidium will only react when our specially designed vial dissolves in the water, which gives John a few crucial seconds to get into our safety zone. Yes!
Wow.
That is more like it. Only on Brainiac do you get that kind of science. But I believe we can go one better. There is one more alkali metal we can legally use.
Yes, Richard, cesium, the emperor of alkali metals, particularly nasty, could go off at any time.
And that's it.
Oh, yes.
Brilliant. I like it already. Now, what's that going to do when it hits the water?
Imagine a depth charge in a bathtub.
Fair enough, mate. I'll leave you to it. Good luck.
Thank you.
Okay, John, go for it.
Warning, 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 extreme danger, clear the area.
As our cesium sinks in the water, the rapid generation of hydrogen gas should produce quite an explosion. And it does. Magnificent. And I think that concludes today's experiment. There is, I should say, one more, even more reactive metal, francium. But for some reason, they wouldn't let us have any of that. Still, there you go. Today's lesson.
Never mixed alkali metals with water.
So why did we just watch that video? It's not just because explosions are awesome, it's because the video demonstrates different elements' reactivity based off of trends that we can actually see in the periodic table. For example, they put rubidium into a bathtub full of water and it immediately reacts. This is because it's in the bottom left of the periodic table. Since it's in that area, it can have its electrons easily stolen from it. And since it's an alkali metal, we know it's highly chemically reactive. This is due to the fact that it has a very low ionization energy and a large atomic size. So you should have this wrapping up trending note taker out in front of you, and we're going to work through a few questions to analyze our thinking about these new trends. First, do large elements have large or small ionization energies? Well, if we look at the pictures at the top, and I encourage you to draw your own arrows on them, the one on the left describes atomic radius, which we know is the largest in the bottom left-hand side of the periodic table. And the picture on the right describes ionization energies, which is largest in the upper right-hand corner of the periodic table. So, do large elements have large or small ionization energies? Well, the larger the element, the smaller the ionization energy, since our trends move in opposite directions on the periodic table. Our next question is, which is larger, sodium or chlorine? If we look where they're located on the periodic table, we can see sodium's all the way on the left-hand side and chlorine's all the way on the right. We know atomic radius increases down and left, which means the further left it is on the periodic table, like sodium is, the larger it is. Therefore, sodium is larger of the two. Looking at size and ionization energy, which element would be pulling the electron from the other, sodium or chlorine? Well, let's look back at our periodic table. We know where they're located. We also know the ionization energy increases up and to the right. Since chlorine has a higher ionization number, it's going to be able to pull an electron away from sodium. It takes much more energy to pull electrons away from chlorine with a high ionization number than it does from sodium with a lower ionization number. Therefore, looking at those two sizes, it's going to be chlorine that's pulling the electron away from sodium. If two elements are similar in size, like hydrogen and oxygen, do they have similar ionization energies? Well, let's look where those are on our atomic radius. So we can see hydrogen's in the upper right, oxygen's over on the, or hydrogen's in the upper left, oxygen's in the right. And remember, the further an electron is from the nucleus, the easier it is to pull it away. But when we actually look at the sizes of hydrogen and oxygen, they're pretty similar. Hydrogen only goes to one energy level, oxygen only makes it to the second energy level. These atoms are pretty similar in size, relatively. And if the atoms are similar in size, then they're going to have similar ionization energies. This is because if their valence electrons are relatively close in distance away from the nucleus, then it's going to be about the same amount of energy to pull those valence electrons away. So yes, if two elements are similar in size, they will have similar ionization energies. If a pair of atoms have similar ionization energies, will one take an electron away from the other to make an ionic bond? No, they will not. This is because if they have similar ionization energies, neither one is stronger than the other to be stealing electrons away from each other. But can they still make a bond? Yes, they can, and they will make a covalent bond. To remind you what our two different types of bonds look like, ionic bonds is where one electron is given away to another, or when you have a higher ionization level and you can steal an electron from something with a lower ionization level, versus a covalent bond is a bond where electrons are shared between atoms. So we can see in water where hydrogen and oxygen share their electrons, versus in salt, chlorine is taking away an electron from sodium. This also leads us to looking at bonding and trending in the periodic table, which can help us now determine if a bond between two chemicals, which creates a chemical formula, is either an ionic or a covalent bond. So what we're going to do together is we're going to identify the oxidation numbers, we're going to draw the Lewis dot structures, write the chemical formulas, and determine whether or not something is ionic or covalent based on that information. For sodium and chlorine, we know that the oxidation number for sodium is +1, and since it's in group 1, it only has one valence electron to put on our Lewis dot structure. The oxidation number for chlorine is -1, and it has 7 valence electrons since it is in group 17. We know that sodium is going to have to give away that electron to chlorine, and we're going to have a simple chemical formula of NaCl. Since chlorine is taking an electron from sodium, and we know this because chlorine is on the right side of the table and sodium is on the left, and chlorine has a higher ionization level. If there's a bigger ionization level for chlorine and it's taking that electron away, it must be forming an ionic bond. Let's look at carbon and oxygen. Carbon, remember, is tricky. It can have an oxidation number of either plus or -4, and its Lewis dot structure has 4 valence electrons. The oxidation number for oxygen is -2, and there are 6 valence electrons. We have a chemical formula of CO2 because it's going to take 2 oxygen to even out with the potential +4 oxidation number of carbon. If you have 2 oxygens, you'll have enough electrons to go around. This is a covalent bond because since carbon and oxygen are so close to each other on the periodic table, they have similar atomic sizes, similar ionization numbers. This means that they're going to share their electrons. Sulfur and fluorine, well, sulfur has a -2 oxidation number. Fluorine has a -1 oxidation number. To determine the chemical formula of this, we have to look more than just the oxidation numbers to determine how these are going to fit together. So I'm going to show you how do you understand a chemical formula only using Lewis dot structures. Here we have sulfur, we have fluorine, the -2 oxidation number for sulfur, the -1 oxidation number for fluorine. Just based off of these oxidation numbers, we know we're going to have some sort of combination of more than one of these atoms in order to create a bond. So if we draw sulfur, we have 1, 2, 3, 4, 5, 6 valence electrons because it is in the 16th group. And when we draw fluorine, We have 7 valence electrons since it is in the 17th group. Now this is tricky. These don't automatically just go together to form the rule of 8. We have too many valence electrons to try and only have a few of each. So this is how this works. Sulfur can give 1 electron to one of the fluorines, but it's going to need another to give its second electron to, then its third electron, its fourth, its fifth, and its sixth. Once there are 6 fluorines to bond with, sulfur will be able to give away each one of those. So one of those electrons is going to go to the first fluorine. We have the second one, the third electron, the fourth electron, fifth, and sixth. What you see here is that fluorine is happy because it has all 8 valence electrons, and sulfur is happy because it's been able to give those and share those electrons. So we get a chemical formula of SF6, which is a chemical called sulfur hexafluoride. So if we come back to our table here, we also know that this is a covalent bond because sulfur and fluorine are so close to each other on the periodic table. Similar atomic radius, similar ionization numbers, they're going to share those electrons. Carbon and hydrogen is going to create CH4. This is because as those electrons are being shared to make a covalent bond, we're going to need 4 hydrogens to match up with the 4 valence electrons carbon already has. Once it's sharing those electrons, hydrogen is happy with 2 valence electrons and carbon is happy with 8 valence electrons. Last, we have potassium and phosphorus. We have our oxidation numbers, our Lewis dot structures. This is going to create potassium 3 phosphorus. We're going to need 3 potassiums in order to match up with our -3 oxidation number of phosphorus. This is an ionic bond. We know this because potassium is all the way in group number 1 on the left side of the periodic table versus phosphorus is in group, let's see, 1, 2, 13, 14, 15. It's in group 15. They're very far away from each other. Phosphorus is going to have a higher ionization number. It's going to want to take those electrons away from potassium. All right, that concludes my lesson for today. What you need to do to complete your work for today is do the self-quiz that is on the back of this note taker. You can complete the quiz on paper first if you like, but in order to receive credit for this assignment, you must complete the Schoology quiz. It is called Self-Quiz Wrapping Up Trending, and it can be found in the bonding folder in your materials. You must complete this by the end of the day on Friday in order to receive credit. So you know the 2 assignments that are due. If you didn't finish periodic trending on Monday, take time to complete that today. Complete your self-quiz, and don't forget about your PhET project that you should be working on. I'm here for you, available to communicate on Google Hangouts if you have any questions about anything. And good luck. Have a great rest of your week. Happy learning.